should I make everyone take a photo of it first?
It's on the course shop.
No, just
I was gonna like,
no. Post them around campus.
like right now?
No, after.
Yeah, I'll post them around.
Okay, guys, let's do just a couple of problems and then we'll get done. Okay. It is found that when a dilute gas expands, okay, so you'll encounter this expression often. Whenever they say dilute gas, what they're implying is that the gas behaves like a ideal gas. Okay, so PV equal to nRT, all those formulae apply. Expands quasi-statically. So it's a slow process. Quasi-statically means it's a slow process, and all intermediate steps are equilibrium states. Okay. So on a PV diagram, you're going along a smooth curve as well. Okay. So each intermediate step is an equilibrium state. Expands quasi-statically from 0.5 to 4 liters. It does 250 joules of work, assuming that the gas temperature remains constant. So if the gas temperature remains constant, what does that mean? Isothermic, and also the internal energy is also constant. Okay. How many moles of gas are present? Okay, so let's see, delta E equal to Q minus W. This delta E is 0. Well, I don't know if this is relevant, but so the amount of heat added is equal to that. Okay. All right. Okay, the work done during an isothermal process is nRT log V final over V initial. Okay. So we know the work done, we know the temperature, we know this, so that'll give us the number of moles. Okay, so this initial part was not needed. Okay. So the number of moles of gas is 250 joules. R is 8.314 joules per mole per Kelvin. Temperature is 300 Kelvin. And log. Now we don't need to convert the volume because that's a ratio, and we can keep it in the same units. So 4 liters by 0.5 liters. And all the units will cancel such that this works out in moles. And so this so 0.048 moles. Okay. So that's the number of gas molecules you have. I mean, that's the number of moles you have. 5/100ths of a mole. Yeah. Two monoatomic ideal gases. So monoatomic ideal gases, what are those? Noble gases. So 2 of the gases there. That also tells you how many number of degrees of freedom do they have? 3. Very good. So CV equal to 3/2 R. So whenever they say stuff like that, they're telling you a whole bunch of stuff. Okay. A and B are at the same temperature. What does it tell you that when they're at the same temperature? Their average kinetic energy is the same. So as you go down on that periodic table, as you go down, the molecules are getting heavier. Since their average kinetic energy is the same, they're traveling slower. Okay? So you put a bunch of those gases in this room. The temperature would be the same. The average kinetic energy will be the same. The heavier molecule will be going slower. Okay. If 1 gram of gas A has the same internal energy as 0.10 grams of gas B, what are the ratio of the number of moles of each gas? Okay. The ratio of the atomic masses of the two gases. Okay. So what we know is the temperature is the same. So 1/2 MA VA square, and there's the average, and I'm going to dispense with the average symbol, but okay, so that's what they tell us. 1 gram of gas A has the same internal energy. Okay, so the mass of the gas is the number of molecules of the gas times the mass of each gas. Okay. So Na equal to M divided by Ma. So the internal energy of each gas is 1/2 okay, this is the internal energy of this gas, and okay, so what they tell us is the mass of gas A divided by mass of gas B equal to no. Oh, I need a better notation. Oops. No. That's mass of gas A molar, that's the mass of one molecule. This mass divided by the mass of a single molecule gives you the number of molecules. Okay, that's what that is. Okay, so this is the mass of gas A, this is the mass of gas B, which is NaMa divided by, and that is 10. Okay. So the ratio of the masses of the gas. And so and what else do we have? The internal energy has the same internal energy. Okay, so this is the internal energy of gas A. This is the internal energy of gas B. Okay, from this equation, what we have is Na over Nb. So for the same internal energy, Na 1/2 M. I'm making a mess of this guy. Okay, I'm missing something. The same temperature. Okay, this is equal to 3/2 kT. Na times 3/2 kT. Okay, so if they have the same internal energy, so the number of molecules is the same. And so 10 times the mass of gas A has the same number of molecules as 1 gram has the same as 0.1 gram of mass B. So essentially what this amounts to is, so N A times mass of A equal to NB times mass of B equal to 10 times NB mass of B. So each atom of A is 10 times as massive as B. Okay, that's what that means. Okay, the ratio of the number of moles of each gas and the ratio of the atomic masses of the two gases. So the ratio of number of moles is 1, that is A, and this is B. Okay. So they are the same number of moles, and the mass is 10 times as great. So what are the masses? Helium and argon. So helium is 4 units and argon is 40 units. Okay. Those are the two gases. All right. We will stop here.